Hello, welcome back everyone. So we continue our lectures. So we have two remaining lectures. So one is today, the atomic physics. Atomic physics, and then we have a nuclear physics. Okay. In the beginning, I include this topic to quantum materials. However, I think it's better to split it out because it's for clear topics, and we can cover it in like 1.5 hours. Okay, so it's only one lectures that to focus on this. Okay, let's start for the atomic physics. Okay, at first we're talking about the atomic spectra. So in the 18th centuries, we start to know the spectrums. Okay, so there are several experiments to show the spectrum. So for example, if you have let's say a hot gas, then the light from the hot gas is passing the grating. Okay, and then it's go to the prisms. Okay, and then on the screen you're gonna see like the light. Okay, and this is the spectrums. Okay, so this is what we call the emission spectrum. Okay, or in the different way is that you put the white light, okay, shining to the gas, and then somehow you have the screen. Okay, so when you have the white light, you have the full spectrums. Okay, so you have like a color, the rainbow color here. Okay, so it's like whatever. Okay, this is just an example. And then due to the absorptions that can happen in the gas, you're gonna have like a black light. Okay, so this is what we call the absorption spectrums. Okay, so in the topic of today, we discuss about how we can model the gas, how we can model atoms that can explain these kind of the spectrums. Okay, for example, you see the hydrogen atoms, you see clear 4 wavelength. Okay, so how do we explain this one? Okay, but it's go to deep questions that how can we model the atoms properly, and when we can explain the hydrogen atoms, and not also hydrogen, but also another gas also. Okay, so the story start with the Balmer. So Balmer tried to formulate the formula that explain the spectrum from the hydrogen atoms. Okay, why we start with Balmer? Because in Balmer, it's the spectrum. It's dealing with the visible spectrums. Okay. So it should be the first thing that we are talking about, right? Because you can see it. Okay. So in that time, Balmer proposed what we call the empirical formula. So the empirical formula, it's the formula that's formulated from the experiments. Okay. In the Balmer formula, so he has the lambda equal to b n square divided by n square minus m square, where m is equal to 2, n is larger than m. Okay, and both are integers. This is what Balmer proposed. Okay, so he said that from the light, that we see here, it's connect to one wavelength, which is the B. So the B is its constant wavelength of 394.50682 nanometers. Okay, and with this wavelength multiplied by the fraction of kind of the integer that doing something, so u square of something divided by square of that thing minus m square, you will get the wavelength that explain the hydrogen atoms. Okay, and then after that, so this I think happened in 1985. Yeah, and then in the 1888, Rydberg, okay, these guys, Rydberg, try to generalize the Balmer formula. Okay, so what he proposed is 1 over lambda, it's 4 over b, 1 over 2, 2 to the power of 2 minus n over 2. Okay, and this 4 over b, we call it the Rydberg constants. Okay, and this is the case for the n larger than n equal to 3, 4, 5, and so on. Okay, so this is the Rydberg formula, and this is Balmer. Okay, but both explain the same thing. So they try to deal with the spectrums. Okay, and then for the Rydberg formula, it's not applied only for the Balmer, but also the different series of the spectrums. Okay, so you can see that this you have the factor of 2 over 2. If you change that, it's become the different series. Okay, so you have Lyman's, you have Balmer, you have Paschen, brackets, and Freund. Okay, and so we use the proper one. So for example, the Balmer, it's using m equal to 2, but for the Lyman, you use n equal to 1. This is m equal to 3, 4, and 5. Okay, so you change these numbers to this thing. Okay. Okay, so we now try to models. Okay, so the model come from Bohr. So Bohr model of the hydrogen atoms. Okay. So in Bohr model, so this is kind of classic model. So we talking about the sun, and then the earth, it's let's say circulate around the sun. Okay, so this is the same as the Bohr model. So electron, it's pull around the protons. Okay, and in a perfect circular orbit, and this attract by the Coulomb force. Okay, since the proton it's much heavier than the electron, so the proton move very little, respond to the force of the proton to the electrons. So we focus on the moving of the electrons only. Okay, but there are some key point of the Bohr models. So the first one, he said that the only certain electron orbits are stables and has no radiations. So what does it mean? It means that when electron is traveling in the circular orbit, it has the accelerations. Okay, and when the charge have the accelerations, it's gonna radiate. Okay, this is it's not what covered in our class, but let's imagine for the circular for the circular motions. So you have the electric charge is moving like this, and then it start to turn, right? So when it start to turn, from what you learn is that the momentum will not conserve, right? Because the particle moving before and after its turn, the momentum is not equal because the direction is not the same. So what's going to happen is that it needs something to radiate from the difference, to radiate something that go out from when the charge is turned, okay, and to make the momentum conserve. Okay, and this radiation will reduce the energy of the particles. Okay, get it? Okay, so it's time to turn. When it's turned, it needs to radiate. Okay, and that radiates. It's reduced it's decreased the energy of the particles. And this is a key point of the circular accelerators, or what we call the synchrotron radiations. Okay, and this is kind of radiation that we can use for several things in several applications. Okay, if you remember the lectures I give it on the special relativities, these accelerators. So you inject the electrons, and electron circulates, okay? But during the circulation, we need to have this thing called the radiofrequency cavity. So this pump the energy to the electrons. Okay, increasing the energy, increasing the momentum, not the speed. Okay, speed is close to the speed of light. I hope that you remember. So we need to have this thing. So because when electron it circulate, it's gonna radiate. So it has less and less energy. So we need to pump the energy into the electron. So try to make it has stable energies. Okay, so this is a key point. That what I'm saying. That for the Bohr model, the electron need to orbit in a stable orbit, and there is no radiation because there is no radio frequency in the way to increase the energy of the electrons. Okay. The second one is that the atoms emit the radiations when electron make a transition from more energetic states to the lower. Okay, so let's imagine you have the state of the electrons. So this is a state I, and this is a state F, which is lower. So both are stables. Electrons, when it's go down, it's gonna radiate. Okay, and these radiations, EI minus EF, it's going to equal to the HF. Okay. So it's quantized. It's depend on the energy of the state I and energy of the state F, and equal to the HF. Okay. The last one is that the size of the allowed electron orbit, it's determined by the conditions imposed on the electrons' orbital angular momentums. Okay. And this equal to the integral multiple of h bar. Okay, what this point is saying that if you consider the angular momentum, so L, if you remember, L equal to the R cross P, right? So P is mv. So finally you get m electron v r equal, and from Bohr's rule, it needs to equal to the integrals multiple of the h bar. So it's equal to the n h bar. Okay. So this is three key point of the Bohr atoms. Okay. So this is quantized. So let's make the n equal to the 1, 2, 3, 4, so on. Okay, n will not equal to 0 because n equal to 0, it's r equal to 0. So basically each electron and the proton, it stick to each other, and that's not the atomic model that we have. Okay, Okay, so Bohr proposed model. So what the model should be able to do is that it should be able to at least explain the spectrum of Balmers. Okay, because if it cannot explain, there's no point to have that model. Okay, so we're gonna try to use the postulates on the radiation. So the second one, that EI minus EF equal to HF, to explain the spectrums from Balmer series. Okay, why we use the second one? Because for the second one, you have the EI minus EF equal to HF, right? And the frequency, it's linked to the wavelength. So it's Hc over lambda. Okay, so you have the lambda here. So if you can calculate the energy state I and energy at the state F, you can link it to the wavelength of the light that you're gonna see. Okay. So let's start how to calculate this. Okay. So let's start from the total energies. Okay. So the total energy is basically the kinetic energy plus the potential energies. Okay. Kinetic energy, you know that it's half of the mv square, right? And for the electric potential energy, it's basically k q1 q2 over r. So it's equal to the minus k e square over r. Okay, it's minus because q1 is electrons and q2 is proton, which is the opposite charge, so that you have the minus here. Okay. Right. So now we're trying to calculate somehow by. So if you think about, if you're looking on what you have now, so you have half of the mv square, and you have ke square over r. Okay, so what you don't really know is the v square and the r, right? And the r tell you the radius, so that we may use that. So what we need to do first is try to eliminate v square, or try to write it in some form that we can use that. Okay, so since the electron is moving in circular orbits, okay, since the electrons is moving in a circular orbit, okay, so you can find the force. Okay, so it's circular motions, so it's mv square over r, right? V square over r is accelerations of the circular motions. So it's equal to the Coulomb force, the size of the Coulomb force, so k e square over r square. Okay, so it's cancelled, so finally you have v square equal to the k e square over mr. Okay, put the e square back. Okay, so you have the final, like the energy equal to the so you cancel m, right? So half of the ke square over r minus ke square over r. So you get minus of the half ke square over r. Okay. It's minus because we are talking first about the electrons proton bound state. Okay, so it's bound together, and if you would like to have the spectrums, you need to put the energy into to the systems. And when you put the energy in, and if you put the energy equal to this half of the ke square over r, you break the bonding, and then you get okay, and then you get the spectrums of that you would like to Okay, so you try to remove electron out from the systems. So now we need to link, we need to find the relation between energies and the radius. Okay, so the energy is linked to the lambda. Okay, so on one side it's clear. So now you need to link about the radius. So for the radius, you use the third node of the ball. So the size of the angular momentum is equal to the integrals multiple h bar. Okay, so you have the mvr equal to the nh bar. Okay, so you need to place v, right, to get the r. Okay, so what you have is v square equal to the ke square over m. So we do the same. So you you square, okay, m square, v square, it's ke square over mr r, right, equal to the nh bar. Okay, square, sorry, n square h bar square. Okay, so m it's cancel one, so r equal to the n square h bar square divided by mke square. Okay, so this is the radius, and since the radius is depend on the integer you put here, so we take it as rn. Okay, we put the rn back to these equations, so you get the energies. Okay, so finally you get the energies equal to the minus of the half ke square 1 over n square h bar square mke square. Okay, so if you're looking on these terms, h bar square divided by the h bar square divided by mke square, this is what we call the ball radius. Okay, and if you put the mass of the electrons and their charge, electric charge square, so what you want to get is 0.0529 nanometers. Okay, and the symbol, we use the A0 as the symbol for the ball radius. Okay, so finally you're gonna get half of the ke square divided by A0 and the n square. Okay, this number, half of the ke square divided by k0, it's equal to the 13.606 electron volt. Okay, this is just the number because k is constant, e it's constant, a0 you have it already from here. So finally you get these numbers. Okay, so this is the energy of the electrons at n. Okay, so now we have the energies. We can put it back here to calculate the lambda. Okay, so what we have to do, it's basically it's transition from ei to ef, right? Ei minus ef, ei is higher energy, so you get 13.606 ev and then 1 over n I square minus 1 over when f n f square. Okay, right? Yep. Sometimes let's check on the notes. Yeah, sometimes they're gonna absorb the minus to this bracket, so you have 16.606 electron volts nf square minus 1 over ni square. Okay, and then for E it's equal to the hc over lambda, so hc over lambda, so 1 over lambda is 13.606 electron volt divided by hc and this bracket. Okay, and there's no surprise that this one is the Rishberg constants, or 4 over Balmer constants. Okay, so now you can prove, okay, that the Bohr model works for the spectrums that Balmer see and formulated. Okay, okay, you have it now. So what's happened is that even although Bohr model was a triumph, I mean it can make an agreement between the experiments and the theory, the atoms explanations of the hydrogen. However, it still suffer from some difficulties. Okay, so some experimental result Bohr model cannot explain. Okay, one of that is what we call the Seemann effect. Okay, so the Seemann effect is that instead of just giving the spectrum, you try to it exists on the with the system with the magnetic field. Okay, so if you have the presence of the static magnetic field, your spectrum gonna split. Okay, so this is called a Seemann effect. So in the figure, so on the A side, you don't have this is from the mercury vapors. You don't have the magnetic field, and when you have the magnetic field of a kind of different orientation, let's say, you have this the splitting of the spectrums. Okay, instead of this big line, you have this kind of a different thing. So it's a different line. Okay, so this cannot explain in more Bohr model, because the Bohr model is only including the state I. Okay, and this one needs to be integers, so it cannot really explain why the spectrum can be split with the presence of the magnetic fields. Okay, so before the model of the quantum is quantum model of the hydrogen atom has been developed, so there are some, let's say, extension to the Bohr model which also success to explain. Okay, one of that is Bohr-Sommerfeld model. So he said Arno Sommerfeld said that instead of the perfect circular orbits in Bohr model, it is possible that electron can traveling in the elliptical orbits. Okay, and these elliptical orbits will give the different effect, and that can split the spectrums into different lines like this. Okay, so this is known as the quantum degeneracy. Okay, but I think that your key point is that this is the kind of the modifications that can help to explain the Zeeman effect. Okay, we will not go into the detail because we're gonna use the last, let's say the newest model of the hydrogen atom that come from the quantum mechanics instead. Okay. Okay, so we move to the quantum model of the hydrogen atoms. Okay, from what we learned in the in the quantum mechanics that we introduced, we're talking about the Schrödinger equation, right? So in that things we can try to we have the wave equations, and then we try to use the wave form to describe the particles. Okay, so this is the same for the hydrogen atoms, but first we need to put the potential energy, right? Because in the Schrödinger equation, you can have equation like this, okay? But now it's three-dimensional, okay? And the wave function plus potential energy equal to the energy and times the wave function. Okay, so you need to first talking about the potential energy we are talking here. So it's electrical potential energies. Okay, so you have U of R equal to KE square over R. Okay. Yep. So now you're gonna try to solve it. However, you say that you see that the system is different. It's difficult to explain by the Cartesian coordinates. Okay, because we are talking about something in a circular orbit. Okay, something in difference. So try and you see that the potential is also it's depend on the radius. Okay, which this one is square root of the x square plus y square plus c square, for example. So it's difficult to solve this one in Cartesian coordinates. Okay, so we need to so we try to do it in a different way. So we try to do it in the spherical coordinates. Okay, so what you have to do, it's basically changing this one to spherical coordinates. Okay, and for phi, you have phi of the x, y, z. You change it to the theta phi. Okay, and try to solve it. For this course, we will not solve it. Okay, it's more mathematics than the physical meaning. So we would like to focus first in this course on the physical meaning of the result. Okay, but I just let you know that it need to solve what we solve today. It's solving in the spherical coordinates. Okay, and so from the spherical coordinate, you can break this wave function into the what I use, it's yeah, it's just something on the factor of, sorry, just something as a function of theta, and some function as a phi. Okay, so we try to solve the different parts and then combine it together, multiplication of each part. Okay, and solving, so this is a differential equation technique, so you don't need to worry about that if you cannot solve today. Okay, but if it's challenges you would like to do it, use Google. I mean, you can try to find a way to do it. Okay, it's known calculation, let's say. But for the result, if you try to solve these three paths, you're gonna get three quantum number. Okay, so it's N, L, and the ML. And what we're gonna do in this course in the next hour is that try to understand the physical interpretation of that. Okay, let's start from let's looking on a number first. So for n, we call it the principal quantum numbers. Okay, it's have 1, 2, 3, and so on. So this is the integers, any numbers. Okay, so you have the L, which we're gonna call it the orbital quantum numbers. Okay, and it has a 0 from 0 to n minus 1. So it has the n numbers. Okay, and then for the ML, we call it the orbital magnetic quantum numbers, and it's vary from minus L to L. So you have 2L plus 1 allowed states. Okay, so this is a 3 quantum number that you can derive it when you place the Schrodinger equation to the spherical coordinates. Okay, and from chemistry there is the name for the shell. So for n, we call it the shell. Okay, and the shell have the name. So for k equal to for n equal to 1, it's k shell. Okay, and n equal to 2, it's L shell, and m, n, o, p, and so on. Okay, so this is the notation we're gonna use. So the first number, it's what we call the principal quantum numbers. Okay, the n. Okay, so this is the first quantum number is associated with the radial functions. Okay, it's basically describe the electron shell, or let's say the main energy level of the electrons. The value is range from 1 to whatever. Okay, but if you have the higher n, the energy is gonna be low and low. Okay, that's follow in the same way as the Bohr atom. So if you see that if n is large, your energies of that electron is going to be very, very low. Okay. So what you have from this this principal quantum number, you get exactly the same as Bohr. Okay, you get minus ke squared over 2a0 and 1 over n square. Okay, it's minus 13.606 electron volt divided by the n square. Okay, where n equal to 1, 2, and 3, and so on. Okay, so I again say that this is exactly the same as Bohr model. Okay, we reached the conclusion from a different point. From Bohr, he make the assumption that electron is moving in the circular orbits, right? And the radius, it's quantized by the momentum. The angular momentum is quantized equal to the nh bar, and he calculate from that. But for this, this calculation, it's basically coming from the Schrodinger equation, and you put the boundary condition to that. Okay, so it's coming from a different point of view to solve the hydrogen atoms, but you get exactly the same thing. Okay, so the quantum model of the hydrogen atoms passed the first issue, so it can describe the Bohr models, which can describe the hydrogen spectrums. Okay, so it's good that you have you solved that. Okay, so next we're talking about what we call the orbital quantum number L. Okay, so from the classical view, so when we are talking about the something that circulates in a circular uniform motion, we calculate the angular momentum, right? So the angular momentum L equal to the R cross P, and it can be any value, right? It's mvr. Okay, so R can be any value. Okay, but in the Bohr model, so he developed the same thing, but say that the mvr need to equal to the nh bar. So it's quantized. Okay. The direction of L, maybe I should mention that direction of L, it's basically perpendicular to the plane of orbit, right? Because you have these kind of orbits, you have the R, so this is the this is the P, so R cross P, it's something here, so it's perpendicular to the plane of the orbit. Okay. So this is what we have from the classical point of view and from the Bohr model, which is classical but quantized. So in quantum mechanics, we give up about the representation of the electron orbits in well-defined circular paths. Okay, it's not well-defined, we don't really know that, but however, the concept of the angular momentum is still there. Okay, and this come from the solution when we try to solve for the theta path. Okay, I use the f theta, so this is what I'm trying to do. Just to avoid your confusion, so I use this is f and this is g. Okay, but whatever, it's functions of the theta, then it's fine. Then it's okay. Okay. So so we have the solution from this f theta, and that's associated to the orbital angular momentums. Okay. So it's the same as Bohr. So you have the discrete value of the magnitudes of the angular momentum. Okay. So what you have, it's basically the L, it's equal to the square root of L and L plus 1 h bar. Okay. The L, it's equal to 0, 1, 2, and so on until n minus 1. Okay. So this is what you get. The orbital angular momentum and the magnitudes. Okay. Okay, so so you can see that basically if L equal to 0, it's L equal to 0, you're gonna get 0. No, you're gonna have the 0 times 1. So the angular momentum, it's becomes 0. Yep, that's correct. Okay. What do we have? Okay. Before we move on to the result, just to remind that this thing, okay, coming from when you try to solve Schrodinger equation and with the boundary conditions. Okay, this comes from that. Okay, it's nothing about Bohr. It's nothing about the classical point of view. You try to solve it, okay, and you will get this result. So for this number, when you have the orbital angular momentum L is equal to 0, you call the state S. This is historic from chemistry. So when it's 1, it's P, 2 is D, 3 is F, and after that it's alphabetic sort. Okay, F, G, H, I, whatever. Okay, so this is what we call the SPDF in chemistry. And when we represent the state, so when we're talking about the principal quantum number 1 and L equal to 0, you say this is 1s. Okay, the first number 1s, so the first number is N, the second number is P. So the second alphabet is P. Okay, 1s, it's N equal to 1 and P equal to 0. Sometimes in physics, we will not represent this one. We can just say that this is a wave function of the quantum number N equal to 1 and 0. Okay, and you have another two number that we're gonna discuss. Okay, but this is the same. So this is n, this is l. Okay, so you can write it in this way, or you can write it in this way. It's represent the same thing. So it's represent the electron in that state. Okay, if you're talking about, for example, n equal to 6 in L equal to 4, so 6g, right? Because at orbital quantum number L at 4, you use the symbol g. Okay, so this is maybe familiar with several people. Yeah, when we talk about the SPDF, it's you familiar with that already. Okay, but if you go beyond that, maybe it's easier to just write the wave function and with the specific numbers. So you don't need to remember the alphabet and convert it back to the numbers. Okay. Okay, so now you have two quantum numbers, n and l. Okay. We move next. Okay. So as you can see that this topics, it's not a heavy calculations. Okay, but you need to understand the idea behind the model. Okay. Next one is what we're gonna discuss about the orbital magnetic quantum number, or M subscript L. Okay, but first we need to go back when we're talking about the current, and the current circulate as a loop. Okay, and then this loop have the area A with the vector of the A perpendicular to the area. Okay, and in that time you can calculate the magnetic moment. Okay, the magnetic moment is equal to the current times A. Okay, so magnetic moment is vector, and it's equal to the size of the currents multiplied by the vector of the area. Okay, and then I cannot remember. I think this part is you study it before the midterm. Okay, if we place this moment in a magnetic field, it will create the energies of the loop system field, which is depend on the direction of the magnetic moments of the loop with respect to the magnetic field. Okay, so if you place it, let's say you put this thing in the magnetic field B, okay, it creates the potential energies, and that potential energies, it's equal to the minus mu dot B. Okay, so this mu is the magnetic moment, and B is the external field. I think when you study this, maybe it's quick because it's the same concept as when you place something in the electric field, you get UE, and then you have some numbers. And then when you place these magnetic moments to the magnetic field, you get UB, which is the minus of the U dot B. Okay. So these expressions show that the system has its lowest energy, UB equal to the minus mu B, when mu and B are in the same directions. Okay, and it has the highest energy. UB it's plus mu B when magnetic moments and magnetic fields are in the opposite directions. Okay, so we're gonna use this concept to describe the system. Why? Because we are talking about electron which is circulate, right? When you're talking about electron circulate, it's the current, right? Electron, it's moving. The current is just the way that electron is moving. So it's not something special, okay? So we gonna use that, okay? So however, just remember that we already abandoned the circular orbit viewpoint from Bohr theory, okay? So it's not a clear path that electron is moving in the orbit. However, the atom still possess the orbital angular momentum. So it still have some sense that this magnetic moment still exists, okay? So this orbital magnetic quantum number is arrived from the when you try to solve the Schrödinger equation in the phi components. Okay, the solution can explain the result of the spectral line of the hydrogen when the atoms are placed in the magnetic field. So this is it can explain the Zeeman effect. Okay. And the Zeeman effect cannot be explained in the Moore model, but can be explained in the extension of the Moore model, the sum effect. Okay, so you have the electrons, but it's not moving in a circular orbit, but it's in the elliptical orbit instead. But from the quantum point of view, it can be described by the magnetic moment. Okay. In quantum mechanics, there are discrete directions that allow for the for the mu with respect to b. Okay, so there is that discrete direction. If you go back to this one, there are no forcing that b need to be in the same or the opposite. It can be in any orientation. The system will adjust itself. But in quantum mechanics, we are talking about the discrete directions, okay, of mu with respect to b. And since mu is linked to L, okay, so it's mean that the discrete direction of mu, it's translate into the direction of the L being quantized. Okay, so what is the meaning is that when you talking about the let me find the reference bit just to So if we talking about the projection of the L, the projection of L in z-axis, so this is the direction of the directions of B. Okay, it's quantized, so it's equal to the ml h bar. Okay, and this ml is the orbital magnetic quantum numbers. Okay, and the ml equal to the minus L plus 1 and so on until plus L. Okay, go slow. I will go again just to make sure you understand the concept. So electron, it's moving in a circular path, in a closed loop. Let's say it creates the currents. So this is it's create the magnetic moments. Okay, and then when you place this magnetic moment to the B field, it's create the energy of the moments and the field systems. It's create the potential energies. Okay, in classical world, we have no control of this direction. It can be in any directions. Okay, B and mu doesn't need to be the same. It's because we place it. We can place this is mu and this is B, whatever. It's fine. In quantum mechanics, okay, we don't have a clear viewpoint of the electron trajectory orbits, circular orbits. But we still have the concept of the orbital angular momentums. Okay, so we still have the concept of that orbital angular momentum and the magnetic moments. Okay, so the existing of this magnetic moment placing in the magnetic field that you have the energy splitting, so you have that energy add up to the energy we calculate from the principal quantum numbers, En minus 13.6 electron volt divided by n square. Okay, so this thing add up to that. So yes, so that we can use it to explain the Zeeman effect, because you have plus and minus and the same. Okay, the old one, the one without the splitting. Okay. In quantum mechanics, the direction of mu, it's not continuous. It's quantized, and it's with respect to the direction of b. And since mu is linked to the angular momentum, so that the discrete of the mu, it's translated to the angular momentum L being quantized. Okay, and when we say being quantized, it means that the projection of the L in the z-axis or in the direction of the b, it's quantized. So it's equal to the ml, which is the orbital ml times h bar, and ml is what we call the orbital magnetic quantum number. Okay, and the value is ranging from the minus L to L. Okay. The quantization of possible orientation of L, we call this is the space quantization. It's the old word. Okay, sometimes people still use it. Okay, you may know that. You should know two words. So you have the quantizations of the orbital angular momentums, or what we call the space quantizations. Okay. So this is how you drawing the model. Okay, so you have the B field. Okay, and then you have the orbital angular momentum L. Okay, so what we say is that the projection of the L to the B field direction is discrete. Okay, so its projection to be, for example, this is model for the L equal to 2, so the ML run from minus 2 to 2, right? So it's minus 2, minus 1, 0, 1, and 2. And the projection of the L, it have the 5 value. Okay, the projection of L on the z-axis, it's only 5 value. Okay. However, it's important to note that we don't really know exact position of the exact L. Okay. So the vector L, we don't know. We do not know exact directions. Okay, this come from the uncertainty principles. So you don't know exactly the position of, and you don't know exactly the momentum, right? The delta x, delta p, the delta x, delta p, it's larger or equal than h bar over 2. So you don't know exactly the momentum, you don't know exactly the position. So this is the same because L, it's linked to the momentum. Okay. But you know that the LC need to be quantized. So you can imagine that you have a cone. Okay, you have a cone, and this cone, you place the L on the cone side, and then it can go in every directions. Okay, it's just lying on the cone, and it can go. Okay, and this cone, it's just the quantization status of the L. Okay. So you can have the relation between cosine theta, which is the the angle between LC, L projection on Z axis and the L. Okay, so it's basically LC over L. Okay, so it's MLH bar divided by square root L and L plus 1 H bar. Okay, and then that term is cancelled. Okay, so this is the angle between the vector L and the projection of the L on the Z-axis. Okay. In 1921, Otto, Stearns, and the Walter Gerlach. So they performed the experiments that demonstrate these space quantizations. So they show that the space quantization exists. Okay. And as I said, the word space quantization is the old name of the quantizing of the C component of the angular momentum. So the quantizations of the LC. Okay. So what they did, it's basically you have the source of the hydrogen atoms, and then it placing, and then it passing to the non-uniform magnetic field, so you can change it. Okay, and you can select the Z direction of it. Okay, which is the more strongest in the B field. And then you have the photographic plates. Okay, and the expectation is that if you have a classical way, so the angular momentum can place in any direction, you should have this kind of the solid thing, so it's go everywhere. But if it's the pattern that they say, it's like the hollow shape. Okay, so it's not going everywhere, but it just of some direction only. That's mean the space quantization exists. Okay, and with the magnetic moments placing in the magnetic field, you have the potential energy term add up. Okay, and this term can consider to be the source of the splitting of the spectrums. Okay, so before the when we don't have the magnetic field, you have just this is, for example, L equal to one state, and then when you place the magnetic field, the spectrum splitting, so it's splitting up, splitting down, and stay the same, so that you see three lines of the spectrums. Okay, so this show that the quantum model works without modifications. Okay, so you can explain the Zeeman effect from this model. Okay, so the quantum model of the hydrogen atoms. So this is just the order of what's happened. In 1971, Stern realized that he can make the experiments. Okay, Stern and Gerlach were not encouraged by the theorists. So theorists say, yeah, don't do it, to do the experiments, including Born. And after that, Born came around and become the supporters, okay, of the experiments. They're reaching the financial difficulties. Okay, experiment need more time and need more money to complete. So they need like a public series, public lecture series to collect the money for the operations, and they need the support from the private sections. Okay, and finally, Stern and Gerlach confirmed the Bohr-Sommerfeld theory. Okay, and then Gerlach sent the congratulatory cards to Bohr. So this is the postcard, and one side of the postcards, it's showing the experimental result. Okay, and you can say that this is sent to Niels Bohr. Okay, and after the results come out, few weeks, the famous theorists like Einstein or Ehrenfest published a short note on this experimental result. Okay, so this seems to be the end of the story. Okay, you have 3 quantum numbers calculated from the Schrodinger equation, right? You have the quantum number n, you have the quantum number L, and the orbital magnetic quantum number ML. Okay. However, this is not the end of the story. Story still continue. There are the there are the new quantum number arise from the experiments, because physicists observe that the spectra of some gas, like a sodium vapor, instead of a line, there is 2 lines that come very close to each other, and that's what we call the doublet. Okay, in a place that you should have only 1 line, there is a splitting of 2 lines. Okay, and they cannot explain by the quantum number n, l, and the ml. So in 1925, when the doublet was observed, this dilemma. So dilemma is something which is difficult and need to be determined by some alternative thinking. Samuel Goldschmidt and George Uhlenberg, they follow the suggestion by the Wolfgang Pauli to propose the new quantum number, and that's related to what we call the spin quantum numbers. Okay, we're gonna discuss about this when we have a clear picture of the spins. And then in 1927, Phillips and Taylor, so they repeat Stern garage experiments. However, what they use is they use the hydrogen atoms, and this is very important. Why? Because if you place the hydrogen atoms in the lowest energies, okay, so you place the hydrogen atom with n equal to 1. If n equal to 1, the orbital angular momentum is 0, right? And the orbital magnetic angular momentum is also 0. So this is controlled by the quantum model of the atoms. So it should have only one state. Okay, so when you see the spectrum, it should only one wavelength. So they expect one wavelength. Okay, but no, the experimental show that the beam splitting was there. Okay, so this means that these 3 quantum number is not enough. They need something else to explain. Okay, and that is the concept of what Goldschmidt and Uhlenberg introduced. So it's a concept of the spin. Okay. Then 4 years later, Paul Dirac, when he used the relativistic form of the total energy to solve, the spin come out. Okay, and his analysis confirmed that this spin is the fundamental nature of the electrons. It's a fundamental nature of the particle. Okay, so spin, it's like a mass or the charge. It comes or it's born with the particles. Okay, so that's what we call the intrinsic properties. Okay, and for the electron spins, it can have the single quantum number s. Okay, and s it's half. So it have one quantum number. Okay, which is half. Since the spin is the form of the angular momentum, so what we did it for the angular momentum, we did it for spin. Okay, so the spin size, so it's s and s plus 1 h bar. Okay, so it's half and the 3/2 h bar, right? So it's square root t/2 h bar. Okay, so this we have it. So the magnitude of the spin angular momentums. Okay, and what we have apart from this, so this is compared to the L equal to the magnitude of the orbital angular momentum. And what we have is the quantization, right? So the spin also have the quantizations, okay? And the quantization, this is MLH bar, so for spin is the MSH bar, okay? And the MS, it's basically plus half and the minus half. Okay, so the C component of the spin also quantize. The C components of spin is also quantized. Okay. So now you have it, okay? This is what I already write it. So MSH bar, MS equal to the plus and minus half. Okay, with this spin concept, okay, you can explain now the splitting of the hydrogen atom spectrums, okay, with this concept. So in summaries, we now have the 4 quantum numbers, okay, the N, the L, the ML, and the MS, okay. So we have 4 quantum number, and this 4 quantum number is used to describe all the electronic state or the electron state of an atoms, okay. So you have N, you have L, you have ML, you have MS, and now you know the condition, right? So N can be 1, 2, 3, and so on, right? L it's from 0, 1, 2 to N minus 1. ML is minus L plus 1, and so on until plus L. And the MS is plus and minus half, okay, for the electrons. Okay, and you have the symbolic, okay, so you have like 2s, so 2 represent the principal quantum number, s represent the orbital angular moment, angular momentums, okay. So now we have the questions arise. You have the 4 quantum numbers, you have electrons. So if you have elements, so which how can we fill the electron to the state? Okay, for example, we are talking about next from the like from helium, next from the hydrogens, right? So you have for the hydrogen, you have like 1, 0, 0, and plus half or minus half of the MS, for example. The question is that for the helium, if you have 1, 0, 0 plus half, what is the wave function of another electrons? So this thing have 2 electrons, right? It's gonna be 1, 0, 0 and some numbers. And if it's not clear, we're going to next one, like boron or carbon. So carbon, it's C612, right? So you have 6 protons. So you have 6 electrons. The question is that what is the wave function of that 6 electrons? It's gonna be 1, 0, 0, and the last number is random between half and negative of half. But if it's falling in that situation, it's the chemistry that we never know about, right? This is not the nature that we learn, Okay, the chemistry developments never talking about the electron in the same state. Because if it's like this, everything that beyond this n equal to 1, it's become excited and it start to fall to the ground. Okay, it start to fall from, for example, this is shell n equal to 3, it start to fall to n equal to 2, and then it start to fall to n equal to 1, because we allow the electron to be in this state. Okay, because from the second law of the thermodynamics, the entropy needs to be the lowest, right? The entropy increasing, right? The system would like to stay in a more low energy. Less when you talking about the high energy, you need to put more work on that, and that entropy it's try to organize. Okay, so but this is not the chemistry we are talking about. So in 1925, Pauli answered these questions. Okay, so this is called the Pauli exclusion principle. So he said that no two electrons can ever be in the same quantum state. Or in general way, in atoms, you cannot have electrons in the same set of the quantum number. So each electron need to have the different quantum numbers. Okay. And I already mentioned that why this principle it's great. It cannot. It need to be valid, because if it's not valid, the electron, okay, will fall to the lowest energy state. Okay, and that is not atom that we know. Okay, at least we confirm from the chemistry. Chemistry come, let's say it's parallel with the quantum, but it's come before the predict tables come before the quantum theory arrived. Okay, so the quantum theory need to explain also why chemistry is in that way. Okay, so this is an example of the atom that up to the n equal to 3. So n equal to 3, it means can be n equal to, for the n equal to 1, you have L equal to 0, ml equal to 0, and the spin is just up and down, plus half or minus half. For n equal to 2, so L is possible 0 and 1, and L equal to 0, ml is 0. When n equal to 1, L equal to 1, the orbital can be 1, 0, and the minus 1. And each one can have the two possible states of the electrons. Okay. So each shell, each n, you're gonna have the number of the electron is 2n equal to the number of the allowed electron state. It's 2n squared. Okay. Allowed states. Okay, so when n equal to 1, it's possible 2 state. Okay, when n equal to 2, it's possible for the 8th state, right? 2, 4, 6, 8. Okay, it seems to be complete, right? But it's not really complete. Why? If we're talking about, for example, the hydrogen atoms, it has the 1 electron, right? 1 electron. So the wave function of electron can be 1, 0, 0 and half, or 1, 0, 0 and minus half. Okay. For the helium, from the Pauli principles, you cannot have 2 electrons in the same quantum state. So when the helium, you need to have 1, 0, 0, half, and 1, 0, 0, minus half. Okay, and then you start from that lithium. So you place first it's 2 electron in 1s, and another electron in 2s, so it needs to jump. Beryllium have 4 electrons. Boron have 5 electrons. The questions come when you consider carbon. Carbon have 6 electrons, 6 protons, 6 electrons. Okay, so you place 2 of them in the 1s state. Okay, and then you place another 2 in the 2s. So now you have 2 remains, right? So you from 2s you go to 2p, right? When n equal to 2, right? So you have 0, and when you have 1, so you have 3 box. Okay. So in this 2p, you place 1 electron in 1 box, let's say. Okay. What is another electrons? You want to place it in the orbital that have the same number as the first one, like you place it here, or you need to place it in a different box, different orbitals. Okay. So this is a question, and that's answered by the Hund's rule. Okay. So when an atom has the orbital of equal energies, 2p, it's equal energies, the order in which they are filled by electron is such that there is a maximum number of electrons have unpaired spin. Okay, when you fill that, you need to have a maximum number of electrons in the unpaired spin. Electron would like to be, unpaired, no bound. Okay, so you need to fill this one. So with this rule, it guides you that if you have 2 electrons in 2p state, so one need to fill in one orbital and another one need to fill in different orbitals. Okay, and if you have 3, so they span in 3 orbitals, and then when they start to have 4, one box is filled with up and down, and another 2 remains like this, remain independent from each other in a different orbital. Okay, and when you have 5, there's no choice, so 2 need to be filled in 2 boxes, and 1 still remain freely in 1 orbitals. Okay, and when you have 6, they are few, and when they have 7, it's jump. Okay, so this is Hund's law rules. Okay, and from rule of the Pauli and Hund's, that can help you to understand the periodic tables. Okay, the periodic table is invented in 1871, so this is long before quantum mechanics by the Russian physicist Dmitry Mendeleev. Okay, so Mendeleev tried to order the elements, okay, and try to group it in each column. You have the element that have more or less the same properties. Okay, and the when the quantum arrive, the arranging of the electrons in the orbitals, that can get us a clear picture of the why periodic table is like that. Okay, and we can use that partially understand the property of the electric tables by looking on the electron configurations that coming from Pauli's and Hund's. Okay, I say partially because there are some exceptions somewhere in these periodic tables that we need to have understanding in maybe like extension things. Okay, but that is not in the focus of the quantum mechanics at this point. Okay, but in chemistry maybe they teach you on some exceptions, some rules that need to be applied on top of the simple periodics tables rules. Okay, I think this is all for this atomic physics. Okay, we spent almost 1.5 hours for this. As I mentioned, this is not this topic. It's not for calculation, but it's a concept of the atoms that we would like you to understand. Okay, so you need time to digest and try to understand the pictures, understand the meaning of the quantum numbers, and then when we give you the state, you can describe it. Okay, hope you enjoy these videos. So we have one remaining video on the nuclear physics, okay, and one tutorial on the quantum and also of the atomic physics. Okay, thank you everyone. Bye bye.